Hey, this is Mr. Aiden back, and this is AP Calculus AB. We're going to be doing implicit differentiation. Implicit differentiation, it's a lot easier than it sounds, and it's a lot easier than it looks. So sometimes when we take a derivative of something, what are we really doing? Let's say we take the derivative of something like 3x squared. 3x squared. So what's actually happening here is we are taking the derivative with respect to x of this value. So we use the power rule. We could do 2 times 3 is 6. That x to the first power. And it's really times we're differentiating x with respect to x, which you can see dx over dx equals 1 because we're really using the chain rule here. And you can see we never even write this. Why don't we write this? Is because we're already differentiating with respect to x. So we know that it's equal to 1. But using the chain rule properly, that is doing this power rule utilizing the chain rule. So what would happen if we did d over dx of something like 3y squared? Well, 3y squared, we would take the derivative of 3y squared, which would be 6y to the first power. But then, using the derivative, it would be dy dx, which means we can't just cancel this out because we're differentiating with respect to a different value. We're differentiating the y with respect to the x. And so that is where we come with implicit differentiation. You can see right here we have x squared plus y squared equals 1. That's the equation for a circle. And you can see if we wanted to find the slope of the tangent line on any single point on this, we could figure out, even though this isn't quite a function, okay, is we would do what's called implicit differentiation. And so what are we going to do? We're going to do the derivative with respect to x of my x squared plus the derivative with respect to x of my y squared equals the derivative with respect to x of 1. You can see I'm taking the derivative of everything on both sides of the equation. So what's the derivative of x squared with respect to x? It's just 2x. Really, it's 2x dx over dx. The dx over dx cancels out. What's the derivative of y squared with respect to x? Is 2y dy over dx. Does that make sense? Because utilizing the chain rule. What's the derivative of 1 with respect to x? Well, it's 0. It's 0, isn't it? And so what do we have here? We have a 2x plus 2y dy over dx is equal to 0, which means now I can do some algebra. I can move the 2x over to the other side by making it negative 2x. I can divide by my 2y, so a negative 2x over 2y. The 2's cancel out, which means the derivative with respect to x, the derivative at any point, is equal to negative x over y of this function. Okay, and we can plug in different points. Let's say we plug in the point 0, 1. 0 for x, 1 for y. Take a look. The slope of that line is equal to negative 0 over 1. That slope is 0 right here. It is right at the top. The slope is 0. What about let's see. What about at 0.5? 0.5. Okay, so we have 0.5 or 1/2. We plug that in right there into my function. Is we do 0.5 squared. 0.5 squared, that's 1/4. We subtract that, so 1 minus 1, that 1/4. And we're going to square root that guy. I'm just trying to find out the exact point of 0.5 is 0.866, and so on and so forth, dot, dot, dot. Okay, so now I'm going to plug that in. I'm going to plug that into my dy over dx because that's the derivative at any point. So that's negative of my x value, that's 1/2, over my y value, that 0.866, so on and so forth number. So negative 0.5 divided by that answer, I'm going to put that in, and I get negative 0.577, and it goes on. You can see I have a negative slope right here. Now, if we look at 1, 0, and plug that in, my dy over dx is equal to negative x value, 1, over 0, you can see that's undefined because we have a vertical tangent right here. That slope is undefined at this point as well as the -1 point. And so this implicit differentiation works to find out the slope at any point in time of functions where it doesn't say y equals something. It has x's and y's together on both sides. Okay, let me give you an example. Here we have an example. We have x squared plus xy plus y to the third is equal to 0, and we want to find dy over dx. We want to find the derivative of this function. Okay, so I'm going to take d over dx of x squared plus d over dx of xy plus d over dx of y cubed equals d over dx of 0. So what is the derivative of x squared with respect to x is 2x, isn't it? What's the derivative of this function xy? I got to do the product rule, don't I? Okay, so the derivative of x is 1 times y plus x times the derivative of y, which is 1. And since I did the derivative of y here, I do dy over dx. Don't forget that dy over dx. If you forget it, you'll be up a paddle without a creek. Okay, other way around, maybe. And then we have the derivative of y cubed. That's going to be 3y squared, but since it's y, it's dy over dx is equal to, obviously, 0. The derivative of 0 is 0. So what do I want to do? I want to get all my numbers on the other side, okay? I want to keep all my dy dx's over one side. So here I have x dy over dx plus 3y squared dy over dx equals, I'm going to subtract this on the other side, so I'm going to have negative 2x plus y, okay? Or you could have said negative 2x minus y if you distribute that. I'm going to put that in parentheses. So now I'm going to factor out a dy over dx. I'm going to be left with x plus 3y squared equals negative 2x plus y on my numerator. Okay. Then I can divide. And so dy over dx, the slope at any point in time, equals negative 2x plus y all over x plus 3y squared. So what do you want to do? You want to take the derivatives of every single thing. You might have to use the product rule. Not forgetting when you take the derivative of any y, it needs to have dy over dx with it. Group your dy over dx's together, factor your dy over dx out, get everything over the other side algebraically, and that would be the slope at every single point in time. Okay, and so if you took a look at a point here that would work, that's going to give you the slope at that specific point. And so that is called implicit differentiation. We're going to get a lot of practice at this in class. I hope this helped, and I'll catch you on the flippity flop.